Okay, I'll just take over for a second then. The next talk is by Ivelin from the Space Inventor. They have been involved in developing and getting launched a 16U CubeSat to GEO. That sounded interesting to me, and I thought it might be interesting to everybody else to learn how that was done. The Space Inventor, Carl, and I go back a long while. He and I spent many happy nights in Plesetsk trying to launch SETI Express, well actually launching SETI Express, and I did actually spend some nights with him on a train, but that's another story. So that's the background. Okay, can you hear us?
Yes, I can hear you.
Oh, perfect. Okay. Would you like to... I've sort of done an introduction. Sorry, Ian, I've done you out of a job. I'm not sure whether the introduction was good or accurate, but please go ahead and tell us about your project.
Okay, thank you very much. I'll start by sharing my screen. Thank you very much for the invitation. My name is Ivelin Penchev. I'm an AOCS engineer at Space Inventor. It's a Danish satellite manufacturer. I'm sharing my screen now. Please let me know if you can see that.
Yeah, it's fine. It's fine.
It's great. Okay. So as some of you may know, in May this year, we launched our first 16U geostationary platform. And since then, we've gathered some knowledge. So I'm here to present it to you and share some of the lessons we learned from that. So to give you a bit of context, I'll start with a short introduction to who is Space Inventor. Then I'll talk about the mission and what is, so to say, under the hood, what components we have in the satellite, and then we'll dive into some on-orbit data that we've gathered. So who is Space Inventor? We're basically a vertically integrated satellite manufacturer, meaning that we aim to produce all of the components in-house. We are based in Denmark. We've been growing organically without the need of investors since the beginning. And one of the key strengths of the companies is that the same components that go in a 6U or a 3U, they can just be stacked up and be used in a microsat, for example. So with this, it's been a long project, but now I'm here to share some of the specifics of our 16U geostationary platform. What this satellite is doing is performing some bringing to use services, technology demonstration, communication services, and so on. And Space Inventor, we have built it and we are operating it for our customers, for our customer gravity space. So let's look at what is inside the spacecraft. We see some maximum power point trackers, some PDUs, also a battery. Then we can see on the top the thrusters. It's electric propulsion from Impulsion. Then we see some of the reaction wheels and the ADCS module. If I add a little more, we can see a bit of the payloads, that's some cameras. Then we see some of the TD&C for the radios and onboard computers. And the interesting part is that almost all of that, except for the thrusters and the payloads, is something we built in-house. And from another angle, we also see the solar panels, fine-sun sensors, hold-down release mechanisms. Those are also produced by Space Inventor. So now that you know what comprises the satellite, let's look at how it made it to GEO. So on the ground segment, we established connection with the Cortex at each ground station. We used SSC services in Sweden, Australia, and Chile, which allowed us to communicate with our satellite during the orbit race. So basically, it gave us almost 360 coverage wherever the satellite was. So the launch was a very exciting moment for Space Inventor. The satellite was deployed approximately 1,000 kilometers under the geostationary orbit. So we had to travel that distance using the thrusters in the end. So we had a tight schedule when we were launched because of the delay of the launch. So we had to optimize the orbit race to get the designated slot as soon as possible. So we decided to operate on a duty cycle. As you see here on the thrust graph, we are thrusting for about 20 minutes, and then for 10 minutes we're charging the batteries, and we allow the thruster to cool down, because electric thrusters they get to heat up pretty quickly. So then we also, of course, have several thrusters, so we iterate between the thrusters also to balance out the fuel and to allow the thrusters to cool down more. And then, just to give you a bit of perspective, this is the graph of the thrust during the whole orbit race, which is, as you see, almost uninterrupted 2 months and 10 days of thrusting, which is something we're really proud of, because it showed us that our basically out of the box, it took us a month to commission the satellite, and then those 2 months of orbit race was a nice test for the whole system. While burning, we also had to adjust the burn direction slightly, so the thrusters, they allow for vectoring of the thrust vector, so this way we can also desaturate the wheels while we are doing the orbit race. And every time we are in those 10 minutes of charging, so as you see here on the bottom graph, we have the thrust just ending, and then we have 10 minutes of basically charging, and then we start thrusting again. So that of course means that we are changing the attitude twice every half hour or so. So that in the end means that for the whole orbit race, that is about 6,000 attitude changes, which was putting our ADCS system to a very good test. So talking about the ADCS, let's talk about the performance of the controller. So we tuned it to be able to perform those quick transitions every 10-20 minutes, but at the same time also not doing it too power in a too power negative way. So we kind of went for a more balanced controller, and that gives us about 1 to 2 minutes of stabilizing after attitude change. So this peak here that you see is one of the attitude changes that we had to perform. So if we now zoom in on this area, so looking at a more zoomed in graph, you see that the first side is when we desaturate, and we do, so that's where the thruster is burning. It's also expected that we have some higher error there. Then we have the attitude change, and then we see the beginning of the sun tracking. So you see that even when we didn't actually had to go for a very precise pointing, we still were happy to find out that the perceived error goes down to about 30 to 50 arc seconds when not burning. So that was something that was that we're also really proud of, and the way we achieve that is of course to a huge extent that depends on configuration and software and other things, but to a huge extent it's due to the high precision of our hardware in terms of the star tracker, which gives us the attitude, and the reaction wheels, which are the main actuator, of course, in this pointing mode. Both of them are produced in-house, so that is why we also take a bit of this success story also back to production. So the whole journey, we can of course talk for hours about all the lessons we learned, but on a very high level, the orbit race was something that we experienced for the first time. This momentum dumping with the thrusters was interesting because it takes also into consideration some offset to the geometrical center of mass, and so we had to find that zero torque vector for each of the thrusters. The controller was a nice finding, just to gives us a perspective of how much controller we talk about when we get to GEO. One interesting thing to notice is that the 3 ground stations, they were not equally performing the same. So for example, the one in Chile was a smaller antenna, a smaller dish, so we actually could not perform full duplex. We could not transceive and receive data. Send and receive data at the same time. So there we had to adjust a bit of the radio settings to be able to communicate with the satellite. And of course, one of the interesting things is the thrusters. So this is a very how to say, innovative product, the Impulsion AR3 thrusters, because they are electric propulsion, which allows for vectoring. And from what I hear, I think out of 5 or 6 in orbit, 4 of them are on our gravity, on our satellite. So it's also a very, very new thing. So it was also a great success for them to verify their product. And just to summarize, basically this is the NORAD data of the orbit race. So you see we were launched to deployed about 1,100 kilometers under GEO in May, and then on 6th of June we began the orbit race, and that took about 2 months and 10 days, and it was very successful for us because 10 days later it would have been too late. It would have been too late to get into the slot. So that was a great timing as well. And interestingly, we found out that for the whole orbit race, we only used about 3 to 4% of the fuel that we have on board. So there's a lot more now left for switching between slots and whatever else, station keeping and so on. And if that is not something very impressive for you, we're actually right now we're working on a concept that will be able to get satellites from LEO to GEO in about less than a year, maybe 8 months or so. It's still on a very conceptual level, so I cannot answer a lot of questions about this, but it's something interesting that we're working on because we find that our customers have actually pretty hard time finding a launch for their GeoSat satellites. So with this, we'll be able to get there, maybe not faster, but at least in a more accessible way. So making it a bit easier for customers to do also GEO missions. And that was it from me. Thank you for your attention. And we can go back to some of the slides if you would like. Maybe the lessons will be a nice summary of what we've been talking about. So please ask if you have any questions.
Okay, thank you very much, Ivelin. Does anybody have any questions? Okay, I'm going to wander around the room.
Thanks very much for the presentation. Could you give us some sort of idea how the various RF payloads performed? You've clearly got quite a good handle on positioning the satellite with that degree of accuracy. How did the commissioning of the RF payloads go in terms of pointing towards the right place?
Yes, I'll go back to maybe one of the pictures where we could see the horns. So it's actually a very, very interesting question because right now we are in the process of commissioning actually next week, we're commissioning those horns here. I think is I'm not a radio guy, I think it's the KU and KV band. For the X band, that's the only thing we've commissioned after using S band. So I cannot really talk much about the horns, but with the X band we didn't have any issues. With the pointing, that was we could easily see that actually attitude was not even that much of an important player. I think plus minus 20-30 degrees was, and that's not. I'm not that much involved in it in the radio test right now, but that was not that big of an issue. Regarding the horns, it's difficult for me to say because it's not something that we have tested. But I could provide you with more information in 2 weeks or so, because that is when we will have the results from the horns. But they do have some opening already, and we do have of course we can point them not just nadir, but we can of course point them to the ground station that we are using. So that should not be an issue, especially with a star tracker of that level.
Okay, thank you for the answers there. Any other questions? Graham.
Thank you, Evelyn. Great little presentation there. I think you've got a lot of us going, ooh, ah. I wonder if, could we? So, can we come back to you, particularly if you're talking about a payload opportunity on a 100 kilo spacecraft going from LEO to GEO? There would be a lot of us who would love to have a payload or two on that. So can you book us in now, please?
It's as I mentioned. This is really just on a conceptual level right now. I don't know how much time it will take to develop it, but I've been discussing with the CEO and Carl. Actually, a lot of you know it. I know him. He was saying that he's on a level of finalizing the concept, but that will be, I think, at least a couple or maybe 5 years before we have a product that we can say that we are ready to perform to basically embark on that journey. I think the biggest player there will be the radiation. We'll have to really put a lot of focus on the radiation tests before we can say that all of the components can survive that journey, because there is some in MEO some places where you don't want to be with all the equipment. But sure, I'll pass on the message that there is huge interest in that.
Okay, thank you for that answer. Any other questions in the room? Any on the stream? Okay, in that case, it's just after 3:30. The next talk is at 4 o'clock, where Phil Crump